We are extremely honored today to have Dr. Mats Larsson as the speaker of today's Provost lecture series. Professor Larsson is at the Stockholm University. He serves as director of AlbaNova University Center that comprises of Stockholm University, the Royal Institute of Technology, and the Nordic Institute for Theoretical Physics. Professor Larsson is a prominent physicist. He is a member of the Royal Swedish Academy of Sciences, and many people were glad to know that he is the chair of the Nobel Prize Committee for Physics. In 2020, next year, Professor Larsson will be the chair of the Nobel Symposium on Chiral Matter, with Dmitri Kharzeev as one of the co-chairs. So I'm going to ask Dmitri to introduce Professor Larsson.
Okay, I will add just a few words to what Minhua already said. So today we are fortunate to have a truly distinguished speaker. One thing I will not do is I will not list all of his prizes, awards, and titles, because it would take up a significant fraction of this evening. Enough is to say, as you have heard, that he is the chair of the Nobel Committee in Physics and the member of the Royal Swedish Academy. What I would like to say is that he made some really profound contributions to the physics of chirality, physics of chiral matter, and he is fascinated by the origin of chirality in the universe, a passion that we share with him. So I would also like to say that he has another passion, which is history. He is, for example, a great expert in the history of the Second World War, but he is even greater expert in the history of science, where he uncovered many unknown facts and unknown connections. And so you are in for a real treat tonight. So the last but important thing which I would like to add is that Mats is not the only celebrity guest that we have tonight. He is accompanied by his wife Victoria, who is a physicist, but who also happens to be a professional athlete and a world champion in powerlifting. Who has many she has many prominent students in Stockholm. Many of them are my friends, and one of his best students is Professor Larsson. So please join me in welcoming Professor Larsson and Victoria.
Thank you very much for these kind words, and I would like to thank the Provost and of course my host Dmitri Kharzeev for the invitation to come here. I had a very interesting day today, visiting Brookhaven National Laboratory in the morning and the physics department at Stony Brook in the afternoon. So as you heard, I mean, this lecture will be not so much about shall we say physics, but the history of physics, and in particular very important years that happened roughly between 1925 and 1933. And so I will cover Paul Dirac and his road to the Nobel Prizes in physics in 1933. And here is of course his gravestone, and with the, he was born in 1902 and died in 1984. And what you see here is the very famous Dirac equation. So quantum mechanics, the new quantum mechanics, was born in 1925. And the decisive paper, really the first paper on the new quantum mechanics, was published by Werner Heisenberg And it arrived on July 29, 1925, to the Journal of Zeitschrift für Physik, and it was published the same year. So this is really the origin of the new quantum mechanics. This paper, if you try to read it, is not so easy to read. And I was quite relieved when I found a quote from Steven Weinberg, very well-known theorist, Nobel laureate in 1979, when he says that if the reader is mystified at what Heisenberg was doing, he or she is not alone. I have tried several times to read the paper that Heisenberg wrote on returning from Heligoland, and although I think I understand quantum mechanics, I have never understood Heisenberg's motivations and so on. So, and he compares Heisenberg not to a sage physicist, but where you can really understand maybe step by step what the person has been doing, but by a magician physicist, where it's just pure magic. You can't understand what he's doing, but somehow the results just emerges. And what happened then in 1925 was that Heisenberg was passing Cambridge, where Dirac was a PhD student at the time. And Ralph Fowler was the supervisor of Dirac. So Fowler obtained a preprint of Heisenberg's paper and gave it to Dirac, who he could read German, but I think it was quite tough reading for him in German. And of course then the additional difficulty with all the mathematics. But very quickly Dirac formulated his own shall we say, the fundamental equations of quantum mechanics. So he understood Heisenberg's paper and he made his own formulation, a mathematical formulation of what Heisenberg had done. And he was not alone to do this. One can say that there were two different developments, one in England by Dirac, the other one in Germany, where Heisenberg in Göttingen, where Max Born and Pascal Jordan first published a paper in 1925, where they, shall we say, they identified what Heisenberg had done one could do with matrices. So that was the beginning of the matrix formulation of quantum mechanics. And then there was also this three-person paper where Heisenberg was also participating, Born, Heisenberg, Jordan in 1926. And as I said, we had a paper of Dirac in 1925. Dirac worked with operators. So there were two different developments here. I mean, we had the operator development of Dirac and the matrix development of the Göttingen people. I should say already now that the Nobel Committee paid very little attention to this and to this. They regarded the origin of the quantum mechanics as being Heisenberg, and what followed from Dirac and from Born and Pascal was just a mathematical framework of quantum mechanics, and this would not qualify for a Nobel Prize. This was very clear. The Nobel Committee in 1927 was composed of the following five people. Alvar Gullstrand was a Nobel laureate in medicine or physiology. Svante Arrhenius, chemistry prize winner in 1903. Wilhelm Mosén was the only theoretical physicist at the committee, and he was really the one who came up with the how to award Einstein the prize without awarding the theories of relativity. So Einstein was awarded the prize for his photoelectric effect explanation. Manne Sigmund was an X-ray experimentalist, awarded the prize in 1925, a Nobel Prize in Physics, and Karl-Heim Gyllenskiöld was, I would say, more like a geophysicist. So these were the five Nobel Committee members in 1927. But there was a big change, or big, but there was a change. So from 1929 to 33, two new members appeared. Hans Pleyel, who was more in engineering, and Erik Hultén, who was an expert on molecular physics. And then these three other people remained. Svante Arrhenius passed away in 1927, Alvar Gullstrand in 1930, so they were sort of out. And these were the five members that worked on the Nobel Prizes during these years. The really key person when it comes to the quantum mechanics was Wilhelm Mosén. He was a mathematical physicist, he was an expert on hydrodynamics, and so it's clear that he had a very solid mathematical physics background, but of course the new quantum mechanics was not so easy to digest, so he had a really tough situation. Before we come into the prizes in 1933, one should recognize that the first, shall we say, quantum mechanics prize was given to Louis de Broglie for his, well, theoretical, for his discovery of the wave nature of the electron. And he was awarded the prize in 1929. But as late as 1928, the Nobel Committee felt that there was not sufficient evidence for the wave nature. But what really tipped them over was the experiment that was done by Clinton Davison. And what he was doing, he was shooting electrons at about 80 electron volt on a nickel crystal and looking at the reflected electrons. And he could see that the electrons actually behaved as, not as particles, but as waves. So this was a rather strange situation in physics, because in 1927, Compton was awarded the prize for showing that X-rays behaved as particles. And now we have Davison showing that electrons, particles, behaves as waves. So this was really a revolutionary time in physics. And as I said, I mean, we can say that this was the wave mechanics prize, the first one for de Broglie in 1929. And later on, of course, that was in the 1937 a prize to Davison and Thomson. Thomson, the son of J.J. Thomson, for their experimental discovery of the diffraction of electrons by crystals. So the theoretical prize came first, and then some years later came the experimental prize. The other development, of course, was Schrödinger's wave mechanics, and he came a little bit later than Heisenberg, published in 1926, of course, the famous Schrödinger equation, and then came and it was realized early on in the Nobel Committee that Schrödinger's wave equation was non-relativistic, and it was recognized that somehow one has to merge special relativity with quantum mechanics. And the first, and here comes the celebrated paper by Dirac, The Quantum Theory of the Electron. And this is where he published his, there were two papers actually coming out, but this is the first one, and this is where he developed the Dirac equation, the relativistic wave equation for an electron. And in 1931, it was not obvious from the beginning. I mean, the problem with the Dirac equation was, of course, that there was these negative energy states that had no, it was first difficult to know how to interpret these negative energy states. And Dirac, for a while, thought that maybe these states somehow correspond to protons. But in 1931, he had realized that there must be something, what he names an anti-electron, an electron with a positive charge. Of course, had never been observed, but this was his conclusion, that these negative energy states that emerges from the Dirac equation has to be somehow associated with an anti-electron. If we look at the nominations for the Nobel Prize, you can see that the nominations in 1928, 29, Schrödinger had in 28, he had 2 nominations, and then he already had 10 nominations in 1929. Heisenberg also had nominations, but not so significant as Schrödinger, and Dirac had 1 nomination in 1929. One can speculate why Schrödinger got more nominations than than Heisenberg. My guess would be that it was easier to digest the Schrödinger equation than the matrix mechanics, which was quite difficult to work with. People were, solving a differential equation, that's one thing, but working with these matrices. Of course, a person who immediately grasped the matrix was Pauli, and I think Pauli was the first one who published the gold standard, the hydrogen atom spectrum, using the matrix mechanics. But I think that the Schrödinger equation and this was more familiar, and that's why Schrödinger received more nominations. Now I'm coming to the mysterious Einstein nomination in 1928. And I'm sure many of you have read this book, Subtle is the Lord, by Abraham Pace, which I think is one of the really great biographies and very interesting. I'm actually rereading it now. I read it 30 years ago, but I'm going back to it now. And in the last chapter of Subtle is the Lord, there is a compilation of nominations for the Nobel Prizes that Einstein did. And I know that, the person he consulted when writing this for the physics nominations was the secretary of the Nobel Committee at that time. And I know that secretary, he knew the archive outside, he knew everything about the archive. So when I read this chapter, I was sure that, of course, this must be correct. This was a nomination that Einstein wrote on September 25, 1928. It's a rather long nomination, and it really speculates about different combinations and so on. But at the end of the day, he's saying here that another possibility would be Heisenberg, Bohr, and Jordan. And in particular, this nomination of Bohr has made its way into the literature. If you look at Wikipedia, it says that Einstein nominated Max Born in 1928, but this was never recognized by the Nobel Committee. If you read Nancy Greenspan's biography of Max Born, she's also coming back to this nomination of Einstein by Born. So why didn't the Nobel Committee recognize Born when he was nominated by Einstein himself? So I decided to take a look at this nomination, and the problem I had was that I couldn't find it in the archive. This is the original 1929 listing of suggestion for Nobel Prizes. Here you have the suggested, this is the nominee, and here's the nominators. So you can see, for example, that the metrologist Bjerknes was nominated here, Louis de Broglie, who actually received the prize in 29. And you can see here, for example, he was nominated by Colson from Leningrad, and so on, Davison, Debye, Heisenberg, and so on. But I could not find a nomination by Einstein. So this was quite strange. I consulted two of the problem was that the secretary of that time, when Pace wrote the book in around 1981, that secretary passed away 3 years ago, so I couldn't consult him. I asked the secretaries that followed him, did you ever hear Bengt Nagel talk about this nomination by Einstein? But they had no recollection. So finally, the mystery was solved by a contact I got with Diana Kormos-Buchwald at Caltech. So as I said, Abraham Pace passed away in 2000, Bengt Nagel in 2016. Nobody else had any recollection of this Einstein letter. But she told me that Einstein's letter was a handwritten draft, and it was never sent to the Nobel Committee. So this nomination of Einstein of Born is a myth. It didn't exist. Einstein never sent this letter to the Nobel Committee. And that also explains why I could never find in the deliberations any reference to this letter by Einstein. This letter will be published, according to Diana, it will be published in the next volume of the collected letters and by Einstein, volume 16, in about 2 years' time. So back to the to what was happening. Well, one could say that in 1930 there was a little bit of an intermission. There was the Raman in India discovered the Raman effect, Raman spectroscopy. And here we have an example of a discovery that transformed into a Nobel Prize extremely fast. So Raman did his discovery in February 1928. It was published in Nature March 31, 1928. He was in 1930 he was nominated by a very strong lineup of physicists and chemists. I mean Bohr, de Broglie, Rutherford, Stark, Wilson, Perrin, all Nobel laureates, and 4 others. So he was awarded a Nobel Prize in 1930. I think the Nobel Committee felt that this was a very good prize. It was easy, it was practical, it was easy to understand. Raman's publications were very, very clear explanations of the effect and so on. And he had a very strong nominations, very strong nominations. But now comes the long march for the Nobel Committee. So after the award 1930, it would take 3 years for the next awards to be announced. This is the longest peacetime gap in the history of the prize. The Nobel archive until early 1960s were mainly written in Swedish. I mean, all the deliberations from the Nobel committees was written, the reports and so on were written in Swedish. There is presently no authoritative translations of all this material, which I think would be very interesting for historians if there was translations. I would say that even for a native Swede, this is not always easy read because it's an old-fashioned style of writing. And sometimes you really have long, complicated sentences and you have to, really try to understand what they mean. I think this is one reason that it has been difficult for historians of science to really understand in detail the Nobel process. If you don't speak the language, you come to the archive, you ask for something and somebody has to translate to you, it's very easy that you misunderstand and you don't quite follow what happened. So, and the archive is open only to members of the academy and after application, historians of science. I should say also that there are actually two types of Nobel archive. There is the real archive with all the originals, everything, and then there is a somewhat simplified archive available to the Nobel Committee, just so that we wouldn't have to go down to the big archive every time we want to check something. We can check it easily. But if you want to really trace the development of a prize like this one now in 1933, you have to go to the original archive. Let's look at nominations. The first nomination I will show you was written by a man where you can see this is his desk in his office. And I took this picture just over a week ago. This is they have preserved completely Niels Bohr's office. And I took this picture and you can see what he has: Faraday, he has Thomson, von Laue, and Galileo. And this is his oldest son that tragically passed away in a sailing accident in the 1930s. So Niels Bohr, he sent this nomination letter. You can see here that it's the famous Blegdamsvej address in Copenhagen. And it's written in Danish. Niels Bohr always wrote his nominations in Danish, his native language, which was no problem for the Swedish committee to read. And for Niels Bohr, he was clear that the first line, person in the first line should be Heisenberg, in the second line, Schrödinger. Possibly one possibility would give them a shared prize. Dirac is not mentioned in this nomination, and Bohr never later either nominated Dirac. He never nominated him. The date here one could pay attention to. The deadline for nomination is always January 31st every year. And Niels Bohr, he sort of fitted this in so that the nomination letter was stamped into the Academy on January 30. So it's a completely normal date for a nomination. Let's look at the other important person now for nominations. A nomination letter written in Kaput bei Potsdam, which is outside of Berlin. This house is preserved. This was the summer house of Einstein. And it has been preserved to this day. And here is now the original nomination letter that Einstein wrote. But the date is very peculiar. I mean, this letter is dated on September 30, 1931. And with Einstein here in Kaput bei Potsdam. And this is a real nomination letter. I mean, here is very clearly going through the logics of his nomination. And I will show you an English translation. I just want to make a point with the date, because to me it doesn't make sense to send a letter in late September when the Nobel Committee has already made their decision. I mean, the only thing remaining is the formal decision by the Academy. So I don't quite understand why he could have waited for just over a month to see who got the Nobel Prize and then made the nomination. But this was not Einstein's style. He just, immediately when he was asked to nominate, he wrote immediately in September. And yeah. So what is Einstein saying? Well, first of all, it's my conviction that two men are in the first line for the Nobel Prize in Physics. Namely, the founders of the wave and quantum mechanics, Schrödinger and Heisenberg. Theories contain a lasting truth, independent work, and so important that the shared prize should not be considered. The question, who should get the prize first, is difficult to answer. He says, Schrödinger's concepts can be carried further, but Heisenberg was first, as I said in the beginning, so that's clear. So forced to make a decision, Schrödinger is given the highest priority. Dirac is not mentioned. The next year, Einstein would write another letter, shorter letter, only putting up Schrödinger's name. So now we come to the problems for the Nobel Committee. The Alfred Nobel's will, dated November 27, 1895, it says, one part to the person who made the most important discovery or invention in the field of physics. This is the rather short line that you have to try to understand what does he mean with discovery or invention. And this is what the Nobel Committee struggled with. In 1931, Osen, April 15, writes a report to the Nobel Committee and discussing what has been achieved with the new quantum mechanics. And the only thing he can come up with, the only discovery of any significance that this theory has resulted in, is the allotropic forms of hydrogen. That's rather bizarre, isn't it? I mean, I tested this on colleagues, even people working with hydrogen. I asked them, what is the allotropic forms of hydrogen? I don't know. This is a chemistry term. This derives from a nomination by a member of the chemistry committee, T. Svedberg, who realized that the physicists were struggling to fit the new quantum mechanics into a discovery. Not just, explaining known atomic spectroscopy, but really try to point that this is a discovery. And the only thing they could come up with was the allotropic forms. I mean, as a physicist, we would talk about orthohydrogen and parahydrogen, just the spins, whether they are misaligned or aligned. But the chemistry language is allotropic forms. Osen, on the other hand, concerning Schrödinger, I mean, what has been gained by Schrödinger's achievement? Well, being an expert on differential equation, I mean, Osen writes that the knowledge that has been gained for ordinary and partial differential equations through 200 years of mathematical research has been put into the service of atomic physics by Schrödinger. And that's what I said earlier also. I think it was easier to digest differential equations than these more strange matrix mechanics. But in 1932, Osen is still fighting with this, and he says that it is obvious that the theorists Heisenberg and Schrödinger personally have not done something that would qualify as a discovery or invention in the spirit of Nobel's will. And that's what he's written here in Swedish. So he's still struggling with trying to fit in this into a discovery or invention. So let's look at the situation. I mean, as I said, in 1930, Raman was awarded a prize. In 1931, no prize was awarded. You can postpone a prize for 1 year, but you cannot postpone a prize for 2 years. So the 1931 prize was lost. The money was not lost. It was allocated to some special fund. But in 1932, the prize was once again postponed to 1933. But now, of course, there was a mounting pressure. The Nobel Committee could not see anything that could be put before the quantum mechanics. But on the other hand, they couldn't fit the quantum mechanics into the discovery. So, in 1933, we have the candidates. We have Schrödinger. As I mentioned earlier, he had 12 nominations. Now he had an additional 29, so he had altogether 41 nominations since 1928. Heisenberg, 29 nominations since 1928. Dirac had 1 nomination in 1928, and then nothing until 1933 when he got 2 additional nominations. So he had altogether 3 nominations. And Pauli, he was nominated in 1933 by Osen. So you may ask, why Osen, who was member of the Nobel Committee, why would he nominate Pauli? The reason is that by nominating Pauli, he made sure that he could keep Pauli in the loop. If he would, when he was writing his reports, would come to the conclusion that Pauli should be awarded a prize, then he had at least 1 nomination, which is the requirement. If you have 0 nominations, you cannot be considered for a prize during a particular year. It's quite interesting to read Osen's report about Pauli, because he recognizes that Pauli is extremely receptive, but maybe not so original. That's his assessment at that time. Pauli would come back. Of course, he got the prize in 1945. Then comes a bit of a surprising letter from William Lawrence Bragg, the younger Bragg, who got the prize in 1915, and of course for his work on X-ray crystallography. And he is now making a very dramatic assessment. He's putting Schrödinger, Heisenberg, and Dirac on the same level. And this was unheard of. You can see here it's a handwritten letter. Dear Westgren. Westgren was Arne Westgren. He was at that time secretary of both the Nobel Committee for Physics and Chemistry. And finally, he is considering a shared prize between Schrödinger and Heisenberg, and a prize alone for Dirac. Of course, this was in 1933, as you could see. It's dated in January 1933. So now Osen had to do something. He had to write a long report on Dirac, which he did in March of 1933. And his conclusion is that when Dirac opened his eyes to the world of science, the most important task to him, without doubt, was the elaboration of Heisenberg's thought. To this task, Dirac spent his life and soul. It has so far not allowed him to create something significantly new. But it's not inconceivable that such activity may come. It is noteworthy that Dirac's most original work is from his recent years. The problem of what Osen had here was, of course, that once again the negative energy states. There was this theory that was new, but it was not correct. Dirac, his equation leads to something that does not exist. So it has to be wrong. This was Osen's conclusion. And what Dirac had done, apart from this relativistic wave equation, was not new. he had worked on Heisenberg's ideas. The same month comes this paper from Carl Anderson at Caltech, where he has studied more than 1,000 photographs of cosmic ray tracks in the cloud chamber, and he has seen something that has a positive charge and the same mass as the electron. And he calls this the positive electron. And he even invents the name. These particles will be called positrons. And this is a name that has been around since that time. This was not the very first, there was a short communication in Science in 1932 from Carl Anderson. But I think people didn't really pay attention to it. I mean, it had a rather strange title about positive bent or something like that. So, but this was clearly a discovery of the positron. Carl Anderson, of course, got a Nobel Prize later in the 1930s for this discovery. So now we're coming to June 2nd, 1933. And now there is a Nobel Committee meeting, and they now conclude that they have to award quantum mechanics. And they conclude that the shortlist is Heisenberg and Schrödinger. They still have to, to consider whether this can be according to the Nobel Foundation statutes. Once again, the discovery problem. But now there was a mounting pressure. There were also members of the Nobel Committee that had recognized that there are predictions by quantum mechanics. For example, tunneling. Erik Hultén was an expert on molecular physics. That was clear one could observe predissociation in molecules. This is a quantum mechanical effect and so on. So that there was an overwhelming pressure now to award quantum mechanics. In June 1933, June 25, Åsén is given the task to write a report on the new atomic physics, and he's discussing the work by Heisenberg and Schrödinger, and this report is used in the Nobel Committee meeting of September 9, 1933. So you see that it's still, at this point, September 9, it's still Heisenberg and Schrödinger who is on the short list. But then comes another correction. So in the next Nobel Committee meeting on September 25, 1933, Åsén has added by hand and Dirac. So what had happened? Well, it was not only the discovery of the positive electron, which Åsén considered as a, shall we say, a qualitative verification of Dirac's theory, but there was also an amendment to the report where Åsén recognizes that two American scientists, Oppenheimer and Plesset, they have converted this qualitative confirmation to a quantitative one. So what they did consider was the irradiation of gamma rays on nuclei, and they could see if they corrected for a pair production, creating positrons and electrons, they got a better agreement with experiments than if they didn't include this correction. And of course, this correction was based on Dirac theory. So this was, to Åsén's mind, a quantitative verification. So now there was both a qualitative and a quantitative, and this sort of tipped the scale. But you can see that the secretary has couldn't read his handwriting apparently, because it's written Gjellet and then corrected to Plesset and so on. And this paper was published in First Rev in the summer of 1933. So now the committee was convinced. So here is a little bit old-fashioned Swedish, but they decide to give the reserved 1932 years prize in physics to Heisenberg, and for the formulation of quantum mechanics and for the use of it in particular the discovery of the allotropic forms of hydrogen. This was then a little bit softened, not in particular, but inter alias or something like that. So it's, but this survived all the way into the citation, these allotropic forms, which I'm sure that nobody would associate with Heisenberg. And then a shared prize for 1933 between Schrödinger and Dirac. And here they have also some correction they for the discovery of new forms of atomic theory and for the use of it, and then they had some handwritten addition to this, and then signed by, for some reason, only 4 members of the committee. Maybe the 5th member was ill at the time or something like that. And the Royal Swedish Academy of Sciences then later on followed this proposal for Nobel Prize. And in these days, the prize was announced in November. And here you can see that 4 new prize winners have been appointed. We have Heisenberg, Schrödinger, Dirac. And this is the first Russian, actually, in literature, Ivan Bunin, who was awarded the prize in 1933. And here one can read that Heisenberg is a warm friend of Scandinavia. Schrödinger does not have the intention to return to Germany. And here is Heisenberg, and of course Dirac and Schrödinger, Ivan Bunin here. And then the day after the ceremony, another Swedish newspaper, Dagens Nyheter, wrote that concerning the ceremony, here is in Swedish, but this is an English translation, then followed one after the other, Professor Schrödinger and young Dirac, who staggered down the stairs in a real old-fashioned professor's white tie, but this didn't prevent Mama Dirac from being somewhat proud, where she was sitting and stretching herself on the 3rd row behind the high-sounding foreign ministers. Only his mother was present. You know, Dirac had a very complicated relation with his father. So, finally, I end this talk with this picture from the Nobel banquet with our physics heroes here and Ivan Bunin here. And here is Dirac, of course. And I just want to end with acknowledgement, the Royal Swedish Academy of Sciences for access to its Nobel archive, and Carl Grandin, who is head of the archive and helped me to find some more difficult protocols. And here you can see him down in the archive and digging in some old material. So with this, I thank you for the attention.
Very much for this beautiful lecture, so we can take a few questions. Please.
Hi. So there was I believe 2 years where there was a delay in choosing who the Nobel laureate would be. What is the explanation for that? Was is there any evidence that there was some sort of disagreement within the committee?
Well, I mean, I think the problem they had was that it was clear that they couldn't find any other prize that would be considered more important than awarding the quantum mechanics. At the same time, they were struggling with how to fit this the new quantum mechanics into the discovery required by Nobel will. I think that was really and that's not only, of course, this committee. I mean, every committee since then have had to have this struggle. I mean, is this really a discovery? Can it be, or is it an invention, or is it, every committee has had this struggle, but it was an unusually long struggle in the early 1930s. So I think that's the answer to it. Yeah.
I'm wondering if we're not in a similar situation today. In your opinion, would there ever be a Nobel Prize given, not for the detection of, but the prediction of gravitational waves?
Usually, we don't speculate about future prizes. So that's difficult for me to answer this question. But I understand the question, of course. But to speculate about future prizes, I don't do that. Yeah.
You showed in the beginning that Heisenberg didn't get as many support as Schrödinger. But in the end, Heisenberg got half and Schrödinger a quarter. So what's tipped the balance? Which members in the committee changed their opinion? Because all of them were in favor of more of Schrödinger than Heisenberg.
Well, you see, the nominations are from external. It's not from the committee. And in 1933, Schrödinger was still ahead of Heisenberg. Schrödinger had 41 nominations, Heisenberg 29. So, I mean, this gap continued.
But why did it change?
No, it didn't change.
Well, Heisenberg got half, wasn't it?
No. You see here, I mean, in 1928... Oh, you mean half the price?
Yeah.
Okay, okay.
There is something which happened in the...
Well, first of all, I mean, it's just not a matter of counting the number of nominations.
No.
And I think that...
Larsson was also interested more
Yeah.
in Schrödinger than Heisenberg.
Yes, I think that the committee recognized that without any doubt Heisenberg was first. So I think they wanted to really point out that he was first. And then came Schrödinger, and then sort of Dirac slipped in at the last minute with the same formulation for Schrödinger and Dirac.
Einstein also felt that Schrödinger should come.
Yes, yes,
So
that's correct.
everybody was for Schrödinger. And
No, not Bohr, not Bohr. Bohr put Heisenberg in the first line and Schrödinger in the second line. So
And one comment, I think the name positron was not due to the editor of Physical Review, but Physical Review letters. But in what you showed, there was a comment by the editor who said we should call it positrons, but the name was earlier given.
I'm not sure about that because first of all, I don't think Physical Review letters existed at that time. This is 1933.
Science, sorry.
The science. I have to go back to that article and see whether, I mean, it's a short communication. I don't think that...
The editor of Science proposed the name, not the author.
Okay. But I think the first time you can see it in print is in this Physical Review article. I don't think positron is named in the science article of 1932 of Anderson. But that I would have to go back and check. Yeah.
Considering cases such as Einstein's or these cases where there's someone or some field that obviously should be awarded the Nobel, but there is some internal contradiction in the committee as to whether this fits with Nobel's vision for the endowment of his prize, how do you see that changing as we go forward in physics towards a more theoretical model of discoveries?
That's a rather general question. I mean, you can see several examples where the theoretical prediction came first, and the experimental discovery came second. I mean, I gave one example, but it's clear that if you want to award a theory prize, there has to be some sort of experimental or observational verification before you can award a theory prize. And this was, as I mentioned, I mean, the Bohr. As late as 1928, the committee was hesitant to award the Bohr. In 1929, they felt that the experiments by Davison, Clifford Davison, for example, and Thomson, that gave sufficient support for the wave nature, and then they awarded the Bohr. But the physics prize, the experimental prize came later, and you can see the same situation in the late 1940s. Yokawa, 1949, I lost the name. Powell, no? The experimentalist in 1950. So.
Next question.
So I noticed that there were two skipped prizes right at the beginning of the 1930s. So was the Nobel Foundation affected by the Great Depression, or?
No. It had nothing to do with that. Nothing. I mean, the money was there. And as I said, I mean, the 1931, the money, the prize was lost, but the money went into some special fund. I don't know exactly what it was used for later on, but the money was certainly there. So it had nothing to do with the depression.
So the nominations process, so these nominations, do they come in, are they solicited?
Yes.
Are they sent by, so how does that work?
No, yeah, I can make a comment on that. They are certainly solicited, but not for, I mean, there are two categories that are always that can always nominate, and these are Nordic professors and Nobel laureates. They have all the time nomination power. But, and then different universities are asked to select persons for nominations. And this, the list of the university is sort of rotating. And then we also have a list of scientists that we ask for nominations, particular scientists. And of course, always interested to get as broad as possible, both geographic and so on, response for nominations. So it's, I think that.
George?
Are there any other good stories of Nobel Prizes that were skipped? I mean, aside from the literature one recently. I mean, the scientific side.
Let's see. I mean, as you could see here, I mean, this process is not easy. I mean, you would think that what could be easier than award Heisenberg, Schrödinger, Dirac the prize? And it was a long struggle, and I think that you can find this. Of course, the archive is closed until 50 years, so one can always go back. If you go back more than 50 years, you can really see. And sure, there are struggles. I mean, let's take the Laser Prize in 1964. It was clear that Charlie Towns was absolutely clear as winner. But should one award also the two Russians, Basov and Prokharov? And there was a very detailed analysis of this by the pioneer in Swedish radio astronomy. And he came to the conclusion that Basov and Prokharov had realized that a three-level system would be preferential for laser action, or maser action actually in their case. And that tipped the scale for the two Russians. So at the end, Towns got 50% of the prize, and the two Russians had to share the other half. So I think that's an example of how small margin you have, and without this very thorough report written by Olof Rydbeck, pioneer of Swedish radio astronomy, Townsend would have received the prize alone. So that's one example.
Okay, two last questions. Yes, the fact that Dirac theory is relativistic, did that help or hurt him in the consideration by the committee, or was it neutral?
No, I think it certainly hurt him until, because they struggled with these strange negative energy states that the theory predicted that hadn't been observed. So I think that definitely was a drawback for him. I think another drawback, I'm sure Osen must have thought, why wasn't he nominated by Einstein or Bohr? I mean, when he was sitting and writing this, I'm sure he had this in his mind. I mean, why didn't they nominate him? And in particular Einstein, I mean, I don't think we have an answer to that. And,
the members of the committee, is there a term limit? And if
yes.
somebody in your committee resigns, how do you select a new member?
First of all, yes, we have a limited term. And
What is it, 5 years?
The maximum number of years you can serve is presently 9 years. Yeah. This is a compromise between, shall we say, it takes some time to get into the work, but you shouldn't stay too long to get too much power. So I think this is a good compromise. The selection, there is always set up a committee in the physics class with the former members of the Nobel Committee looking into the situation. And of course, you try to have as broad competence as possible. There is always 5 ordinary members, but you can add 1 or 2 adjoint members to broaden the competence. And that could, of course, be depending on what type of prize is on the short list.
Is this limited by Swedish nationalities? Committee. Does the committee limit?
We have, well, the committee is not limited. We can have foreign members of the academy as members of if they are active in Sweden. If they are active, they have a professorship in Sweden, they can serve on the committee.
Is there any precedent historically?
Precedents?
Somebody who is not of Swedish nationality serve?
Yes, yes. You don't have to be a Swedish citizen, but when we have had people from, as I said, elected foreign members that master the Swedish language, they can serve on the committee. Yes.
Okay, one very last burning question.
Thank you so much. You've done an amazing job articulating the objective facts about what actually happened, right? Including sort of handwritten notes, answers that are sent. But one thing that's sort of missing from this is, in your discoveries about figuring this stuff out, has there been any sort of emotional reflections personally about any, maybe surprises or things that you've sort of felt about the discoveries themselves that you've looked into personally?
Well, I can put it this way. I can very easily get into the frame of the Nobel Committee at that time, how they struggled. Because this is something that every Nobel Committee has to do. They have to struggle with this very short, discovery or invention passage of Nobel. And I think that's been the case all the time. And so when I sit and read Ossian's writing, I can easily associate myself with him, how he's struggling with how to fit this in and so on. That's very easy to do, yeah.